This is part B of video lesson of autoionization of water. In part A, we just left off where we were trying to calculate the hydroxide ion concentration 0.15 mole per liter solution of hydrochloric acid at standard atomic temperature and pressure. Because we're at SATP, we know Kw is going to equal 1.0 times 10 to the negative 14. We know that our hydrochloric acid is going to completely ionize. So the hydrogen ion concentration is going to equal the concentration of the HCl, which is 0.15 mole per liter. We know our Kw equals hydrogen ion times concentration of hydroxide ion. So we just rearranged and we got the hydroxide ion concentration equals Kw divided by the hydrogen ion concentration. And so then we can just input our values. So we end up with our hydroxide ion concentration equals our Kw 1.0 times 10 to the negative 14 divided by 0.15 mole per liter. I'm just going to come over here to finish. You punch this into your calculator, do it all together. Make sure you put that Kw value in a bracket, and you get the hydroxide ion concentration is 6.7 times 10 to the negative 14 mole per liter. This idea works for strong bases as well, because a strong base is going to dissociate completely in water, just like a strong acid, but this time the strong base is going to release hydroxide ions that are aqueous. So our strong bases, we have two types. We have group 1 strong bases, which when they dissociate, they produce 1 mole of OH for 1 mole of base. That's because if we look, things like our lithium hydroxide here have, for 1 lithium hydroxide molecule, there's only 1 OH molecule. Our group 2 strong bases, though, they are going to produce 2 moles. For every 1 mole of the base. Because these ones have 2 hydroxide ions bonded to the metal, and thus when there's 1 mole of base, there is 2 moles of hydroxide ion released. So we'll look at an example where we want to calculate the hydrogen ion concentration in 0.25 mole per liter barium hydroxide. So we know that our barium hydroxide which is going to be a solid, is going to 100% ionize into a barium ion and a hydroxide ion, except we know there's a 2 here, so it's actually 2 hydroxide ions. So our first step that we want to use is we're going to calculate the concentration of our hydroxide. And I know you can do this fairly easily, but we're going to use a mole ratio because sometimes it doesn't work out quite so nice. So we have our barium hydroxide is in a ratio with our hydroxide ion. We know that it's a group 2 base, so it's a 1 to 2. There is a 0.25 mole per liter. And in case you're wondering where we got this number from, you just look up here. And you're given you had 0.25 mole per liter barium hydroxide. So that's where this 0.25 mole per liter comes from. And it is in a ratio with X. So again, you turn them into a fraction and then you flip it upside down. So we will get 0.25 over 1 is going to equal X divided by 2. So that very easily means we can rearrange that X equals 2 times 0.25. So where X equals 0.50, which means I'm going to squeeze this in right here. The hydroxide ion concentration equals X equals 0.50. And at this point, you need to add your units mole per liter. So now that we have the hydroxide ion concentration, we need to calculate the hydrogen ion concentration. So that's our second step. And to do that, we are going to use our KW expression, so the equilibrium law for water. And we'll rearrange it. So when we rearrange it, we get the hydrogen ion equals KW divided by the concentration of the hydroxide ion. Now it's really straightforward. Just sub in your values. Let's do that really quickly. We know KW. It's just a value that you just need to memorize. We just calculated the hydroxide ion concentration in step 1. So we sub in our values, we do the math, and we get our hydrogen ion concentration equals 2.00 times 10 to the negative 14 mole per liter. And we'll finish this off with a therefore statement. So therefore, the hydrogen ion concentration in 0.25 mole per liter barium hydroxide is 2.00 times 10 to the negative 14. Now those zeros are significant, so you can't drop them. You need to include them. Okay. So now we'll look at our last example where we are determining the hydrogen ion and hydroxide ion concentration and 500 mils of aqueous solution containing 2.6 grams of dissolved sodium hydroxide. So with this type of problem, I think the very first thing you need to do is write out your givens. And I think we'll do that in part C. So we'll finish up part B video and we'll start this problem in part C.